Okay, we've got quite an interesting worked example here in the work energy section. It's quite a tricky one, this, I think, but let's have a look. A package with mass 600 grams placed on a straight metal slide inclined at 17 degrees to the horizontal. Put that there. There's the package. It starts to slide down the hill along the line of greater slope and gains speed as it moves down. Okay, sliding down there. After sliding for 25 meters, that distance down there, it turns horizontal and continues sliding for a further 14 meters until it eventually comes to a stop. There are frictional forces acting parallel to the motion, and all other non-gravitational resistance forces are negligible. And it asks us to find the coefficient of friction between the package and the metal slide and the greatest speed of the package during the motion. Okay, so what we've got is a diagram. Now this is showing the package in its two different positions on the slope and level. So let's just have a look. So I've marked in here the package, and then we put the forces in. Well, the weight, which is mg, is resolved in the direction of motion, which is mg sine 17, and perpendicularly, and we need that because that is actually going to give us our reaction force here. So this is also mg cos 17, and then the force of friction, which I've denoted as FR1 for this part of the journey, is going to be equal to mu times reaction force 1R1, and that's our little equation for friction. F equals mu R. Okay, so those are the forces on this. On the horizontal, it's sort of similar, a bit simpler really, because we haven't got all the weight bears down. There is no weight resolved forward. And the reaction force is just mg again. It's not resolved, so it's just perpendicular to the horizontal. And the friction, therefore, is FR2, which is equal to mu times that reaction force. Right. So that's our kind of free body diagram. What we've got in terms of velocity, it starts at the top of the ramp here at 0 meters per second, proceeds down here. I think intuitively we can say the greatest speed is at this point at the bottom of the ramp, where it's going to be v meters per second, and then it finally comes to rest after another 14 meters here. Okay, so the greatest speed at the bottom of the ramp there. So now how are we going to solve this? Not always obvious with these things, whether we're using kinematics, Newton's second law of motion, work energy and conservation of energy principles, or possibly some combination. So that's spotting that subject of another video. But here basically we've got forces. Well, it says there are frictional forces, so we can kind of rule out it being principally kinematics problem, and we've got these distances here, 25 meters and 14 meters, so this is steering us towards conservation of energy. Right, now the thing is, we've got, for both parts of this journey, we've got unknown v, or at least, for part of this journey, and unknown mu, coefficient of friction. Those are the two things they're asking us. So now there's a recurrent theory thing in a lot of these mechanics problems, is that essentially what we're going to end up with is simultaneous equations. If we can put a relationship together for this first part for v and mu, and do the same thing for the second part, then with any luck we'll have simultaneous equations and we can solve for both unknowns. Right, so let's have a look. So let's first of all look at what's happening on the slope, and as we've already marked on there, the force of resistance equal to mu R1, which is equal to mu times mg cos 17. And the important thing here is that kinetic energy at the bottom of the slide is going to be equal to the potential energy at the top, converted from potential energy to kinetic energy, but we have a loss of energy due to friction. So we have to subtract that out. All right, so we've got an expression for all these things. Kinetic energy at the bottom is going to be half mv squared. Potential energy at the top is going to be mgh. Okay, so mg, and this is the height. Okay, this vertical height here is going to be 25 sine 17, because this height divided by this 25 is going to be sine 17. So, okay, so that's 25 sine 17. And then the work done by friction is going to be the force times the distance, which is going to be mu times the reaction force. That's that. Okay, and we got times mu, and then of course the work done is times the distance. Right, so that is our equation for that, and of course we've got energy, work. I mean, they're really kind of the same thing. Energy is a characteristic of a particle, has energy, and work is what we do to a particle to increase or reduce its energy. In this case, we're reducing it by the work of friction. Okay, so we've got that equation. We'll simplify that out. We get an expression for v squared equals this. Okay, so mark that as 1, because that's going to be 1/2 of our pair of simultaneous equations. When we look on the flat, we've got something very similar, really. The work done in this case by friction is going to be that force times the distance. So, and that is going to be mu times the reaction force times the distance. So in this case, the kinetic energy at the start is going to be, well, there won't be any kinetic energy at the end. It comes to rest. So I haven't marked that in, but I could have written that in. It's the kinetic energy it comes to rest, but that's just 0. So the kinetic energy at the start, it's all used up, all dissipated because of the work done by friction. So that gives rise to this equation. And therefore, half mv squared, this is the same v that we've got on the slope or at the bottom of the slope, equals mu mg times 14. Okay, work done by friction. And v squared equals 28 mu g. So that's our second equation of our pair of simultaneous equations. So we can crash these two things together, eliminate v squared, and we get this equation here. That's that equals that. All right, so well, without just kind of going through it in detail, I think you can follow this through for yourself. If you want to pause the video or whatever, then say we just got an equation now in mu. So if we make mu the subject to the formula and then just solve for that, then we're going to get an answer of mu equals 0.193 to 3 decimal places. Coefficient of friction, obviously no units. Right, well, kind of that's it really. I mean, the next bit to actually find the greatest speed is pretty straightforward, because all we need to do is substitute our value of mu in either of these, 1 or 2. We're going to use 2, aren't we, because it's simpler. And if we just work that through, we get a value of v equals 7.35 meters per second to 2 decimal places. So that basically is it. One thing perhaps we might note here is we've not multiplied anything by 0.6, the mass of the package, because every force and therefore every item of energy or work in there has got in there, and they just cancel out. So so this is actually independent of the mass of the package, which is interesting. They could have not put it in, couldn't they? So it wouldn't have mattered. They might have said it was a mass M or something like that. And it would have all been the same. So yeah, a little bit of confusion factor in there. They've thrown that in. It's a bit of information we don't actually need in order to solve the problem. Right. Okay. So that is it. Hopefully that has been useful.